Hi, I'm Cole.
And I'm Emily.
Today we're learning about how gravity pulls time and how that affects time on different planets.
Whoa, 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 Cole. Slow down. What are you talking about?
I'm talking about T initial equals T final radical 1 minus 2
I think what
gravitational.
Cole is trying to say is we're going to be learning about time dilation due to gravity.
Let's break this down.
This is Earth.
And believe it or not, these lines around it are space-time, which define our perception of time.
The mass of large objects, such as stars, planets, and even black holes, pull space-time, similar to how gravity bends light according to Einstein's theory of general relativity.
The larger the mass, the stronger gravity's pull on space-time. Or, in Earth terms, the more gravity, the slower time passes in comparison to places with less gravity.
Let's check out this example from the movie Interstellar to get a better idea of how this works.
With one complication. The planet is much closer to Gargantua than we thought.
Gargantua.
It's what we're calling them, the black hole. Miller's and Dr. Mann's planets both orbit it.
And Miller's is on the horizon?
Oh, it's a basketball around a hoop. Landing there takes us dangerously close, and a black hole that big has a huge gravitational pull.
Look, I could swing around that neutron star to
No,
decelerate.
it's not that. It's time. The gravity on that planet will slow our clock compared to Earth's drastically.
Oh, how bad?
Well, every hour we spend on that planet will be 7 years back on Earth. That's relativity, folks.
This isn't just science fiction. This is the physics of space-time.
Let's plug these numbers into that crazy equation Cole was talking about earlier. Using this equation, we can determine how much time passes on Earth relative to an hour of time on Miller's planet. Let's break down the variables under the square root. 1 and 2 are constants of the equation. R is the distance from the center of the source of gravity to the center of the planet in question. In this case, the distance from Gargantua to Miller's planet. We determined this distance to be 2.949 times 10 to the 11th meters, roughly the same as the distance between the Sun and somewhere just between Mars and our galaxy's asteroid belt. With the help of an online resource, we gathered the data for M, the mass of Gargantua, also known as the source of gravity, in kilograms. Both G and C are constants as well. G is the universal gravitational constant, while C is the speed of light. Once we plug in all the variables, we find that T of Earth equals 61,320 hours. This means that for every hour that passes in Miller's planet time, 61,320 hours or 7 years pass on Earth.
Given that the film was released in 2014, you've had 7 years, or 1 Miller's Planet hour, to have watched it by now.
But if you haven't, let's take a look at how the results of our equation actually play out in the movie, and how it could possibly happen in real life. Another video.
Hello, Rob?
I've waited years.
How many years?
By now it must be.
It's 23 years, 4 months, 8 days.
Let's look at one more example of time dilation under Einstein's theory of general relativity and what that could look like in practice.
Let's say I live on Earth and Cole lives on a planet far away with much more gravity.
For every 1 of my years, Emily experiences 3 years in Earth time.
And for every 3 of my years, there is 1 year on Cole's planet.
While time is subject to change relative to the gravity which we experience, we individually perceive time the same. For example, we would be able to complete the same number of tasks in our lives, however Emily's life would be long over before my own.
But when I call Cole to wish him a happy birthday once every Earth year, he will actually receive 3 calls from me in one of his years.
Whereas Emily would only ever receive 1 birthday call in every 3 Earth years.
Well, I might feel offended that Cole only remembers my birthday once every 3 years,
He's actually just experiencing time different than I am.
While this may seem crazy, it's a real theory that could have serious implications on our future, and it's only a matter of time before we see it in action.